Episode 10 ended with a real production issue. Checkout app is supposed to run 3 pods, but somehow 5 pods are running. Around the same time, the watch connection broke. The informer recovered. The same key was processed again, and the controller restarted. Any one of these might look suspicious. So instead of guessing, we will trace what actually happened step by step and find the exact moment when the system created the extra pods. The first debugging rule is simple. Do not blame the loudest error. The 5 pods are the symptom we can see. A disconnected watch or a restart may only be a trigger that caused another check. The real cause is the decision that made the wrong change. We must keep those 3 ideas separate. We begin by checking what Kubernetes was actually asked to do. The API server still says that checkout app should run 3 pods. That value was stored, say, at resource version 800, and it never changed to 5. So nobody asked Kubernetes to run 5 pods. The extra pods must have been created somewhere later in the controller's processing. Next, we inspect the 5 running pods. Every one of them carries ownership information pointing back to Checkout app. These are not unrelated pods from other applications. They all sit inside the controller's own management boundary. That tells us the extra pods came through this controller's create path. Now we put the important events in the order they happened. First, Kubernetes stores the desired count of 3 pods. Later, the watch connection is lost, so the reflector fetches the current state again. After that, Checkout app is added to the work queue and the controller checks it several times. During those checks, an API request times out and the controller also restarts. By looking at the events in sequence, we can see which ones were only recovery steps and which one actually led to the extra pods. The first thing we check is the lost watch connection. When the watch breaks, the reflector stops receiving new updates for a short time. But the reflector does not create pods, and it does not change how many pods Checkout app should run. Its job is only to recover the connection and get the latest state again. So the broken watch may have caused another check, but it did not create the extra pods. The next event is 410 gone. The reflector asked for changes from an old version, but that old history had already been removed. The correct recovery is to request a fresh list of the current objects and then start a new watch. That rebuilds the latest view. Compaction removed old history. It did not create any pods. Next, we check whether the informer cache has the correct information. The cache says it has finished syncing and is ready to use. It also shows that Checkout app should run 3 pods, exactly the same as the API server. So when the reflector fetched the current state again, it rebuilt the cache correctly. The cache did not change the desired count and did not cause the extra pods. The same Checkout app key may reach the work queue more than once. This can happen after a retry, another change, or when the controller recovers. But the key only means check Checkout app again. It does not mean create another pod. So receiving the same key again is normal. The controller still needs to look at the latest state before deciding what to do. At this point, the observation path has passed every check. The API server stored the right desired state. The reflector recovered correctly. The informer cache synchronized correctly. The work queue delivered a valid reminder. The remaining question is what the worker did after receiving that reminder. To see the controller clearly, we give each reconciliation pass its own identity. Reconcile 1, Reconcile 2, and Reconcile 3 all receive the same object key. For each pass, we will record what state it used, what action it selected, and what result came back. This connects every pod creation to one specific decision. Reconcile 1 begins when only 2 pods are running. The desired count is 3, so 1 pod is missing. The controller sends one create request, and the API server accepts it. Pod 3 is stored successfully, but the reply is delayed and never reaches the controller. The timeout can be confusing. It does not always mean that the pod creation failed. It only means the controller did not get a clear response from the API server. The pod may already have been created successfully, as it was in this case. So before trying to create another pod, the controller should first check the latest state and see whether the pod already exists. The work queue now sends checkout app to the controller again. This is where the real bug appears. Instead of checking how many pods are running now, the controller simply creates one more pod whenever it receives the key. So during the second reconciliation, it creates pod 4, even though pod 3 had already been created. A few seconds later, the controller restarts. After the restart, the informer gets the latest state again, and checkout app is added back to the work queue. That part is normal. The problem is that the controller runs the same faulty logic again and creates one more pod. Now pod 5 appears. So the restart itself did not create the extra pod. The real problem was that the controller created a new pod every time it was asked to check checkout app. We can now state the root cause clearly. The repeated key was not the bug. The bug was that every key delivery was converted into another create command. The controller never asked how many pods already existed. A normal repeated signal therefore produced a repeated side effect. We can now see what really happened. When the watch recovered, checkout app was checked again. When the API request timed out, the controller tried again. When the controller restarted, checkout app was checked once more. All of these repeated checks were normal. The real problem was that every check caused the controller to create another pod. The repair begins by changing what every reconcile pass does first. It must read the latest checkout app object and list the pods owned by it. It should not reuse the old statement that one pod was missing. Every pass starts with a fresh question: what is desired now, and what exists now? The controller then calculates the current gap. When fewer pods exist than desired, it creates only the missing pods. When the counts match, it does nothing. When too many pods exist, as in this incident, it removes only the excess pods using a consistent selection rule. We also make the create operation safer when a reply is lost. Instead of creating an unnamed new child on every attempt, the controller can use stable child identities such as checkout app 0, 1, and 2. If a retry asks for checkout app 2 after it was already created, the existing name tells the controller that the earlier request succeeded. The corrected reconcile loop is now easy to describe. Read checkout app. List the pods it owns. Compare the desired and current counts. Create missing stable children or remove only deterministic excess children. Finally, update status only when the stored status actually needs to change. Now we test the fix by repeating the same problems. The watch connection breaks again. The old history is unavailable, and the reflector fetches the current state again. The checkout app key reaches the controller, and API request times out. The key is retried, and the controller also restarts. But this time, before doing anything, the controller checks the latest state. So repeated checks no longer create extra pods. The verification is now straightforward. The desired count is 3. The actual count is 3. All 3 pods belong to Checkout app. A retry produces no extra create, and the next reconciliation does nothing. The fix survives the same timeout, relist, retry, and restart sequence. We also improve the evidence available for the next incident. Every reconcile log should show the reconcile identity, object key, desired count, current owned count, calculated gap, chosen action, API result, retry number, and observed resource version. With those fields, the team can rebuild the timeline without guessing. This investigation gives us a simple way to debug similar problems. First, check what Kubernetes was actually asked to do. Then identify which resources belong to that application. Next, put the important events in the order they happened. Separate normal recovery steps from actions that change the cluster. For every change, find the exact reconciliation that caused it. Then fix the first place where the controller acted on old information instead of checking the latest state. The final conclusion is simple. The watch recovered correctly. The informer rebuilt correctly. The work queue retried correctly. The controller reacted incorrectly. Distributed systems repeat signals, so safe controllers must repeat decisions without repeating damage. But the repaired controller soon faces a new problem. The team deploys 2 controller replicas for high availability, but leader election is not enabled. Both replicas read desired equals 3 and current equals 2 at the same moment. Both make the correct decision that one pod is missing. Can 2 correct decisions still create duplicate resources? In the next episode, we will see why idempotency is necessary but not always sufficient. We will explore leader election, concurrent reconciliation, and safe writes when more than one controller process can act on the same object.